we can start. So yes, good afternoon, everyone. Thank you all for being here and participating in the seminar of this afternoon. And today we have with us Valeriya Korol. Valeriya is currently a postdoc fellow at the Institute of Gravitational Wave Astronomy in the University of Birmingham. And during the last years, she's been dedicated to the study of modeling compact binary systems composed of stellar remnants. And furthermore, she's an active member within the LISA consortium in the multi-messenger, multi-band work package team. Valeriya got her PhD in physics from the Leiden University in the Netherlands, and afterwards she moved to the University of Birmingham, where she's currently a postdoc researcher. And today she's going to talk about galactic astronomy with LISA. So please go on, Valeriya.
So thank you again for inviting me. I noticed that you have a quite impressive collection of speakers on your website, and I wanted to add to that collection more of an astronomy talk. So in this today I will show you that one day with LISA we will be able to do galactic astronomy in the same way we are doing it now with stars and observed by electromagnetic observatories. I would like to start by reminding you that we can study the Milky Way like no other galaxy in the universe, simply because we are living in it. But at the same time, our inside perspectives sometimes make it very hard. So for example, it is impossible for us to see the large scale picture of our galaxy. So we have to reconstruct it with the tools that we have. And the galactic astronomers address this problem by defining discrete components of our galaxy, like the bulge that you can see in this cartoon, the disk, and then the halo, and by defining their structural parameters, like their masses and scale radii. So by measuring these parameters, we can place our galaxy in a broader context with other observed galaxies, and we can compare it with numerical simulations, for instance, to test our galaxy formation theories and the lambda ACDM model. However, these scale parameters that I mentioned before are not easy to measure, again, because we are measuring them from inside, but also because it is hard to access some of the regions of the galaxy, for instance, because of the dust extinction. And in addition, the distances that are needed for some of these measurements are very difficult to derive from electromagnetic observations. And with this slide, I'm going to show you some examples of current measurements of the Milky Way total mass. On the left, disk scale parameters and the bars parameters. And what I wanted you to look at is that, in each of these panels, the points and the markers of different shape and color represent different measurements using various stellar tracers and techniques. And as you can see, there is a lot of scatter in all of the panels, and there is no clear consensus on the final measurements. So this is where LISA may play an important role, providing an additional messenger gravitational waves for galactic studies. And moreover, we can combine the two messenger that we have now, electromagnetic and gravitational waves, to build a more complete picture of the Milky Way. So I know that many of you are familiar with LISA, so I will skip upon the basic mission design and status, and I will jump directly on the most iconic LISA plot that shows you the frequency coverage on the x-axis versus characteristic strain. That is the amplitude of the gravitational waves. And here you see the panorama of the LISA sources. So we have the massive black hole binaries that Lisa can see from present day to the cosmic dawn. We have the stellar mass LIGO-like black holes, extreme mass ratio binaries, but I will focus on the purple points on this plot that are stellar mass compact binaries in our own galaxy. And as you can see from here, they will appear in the LISA data as almost monochromatic sources. So they will emit at a single frequency, and here therefore they represented as a point on this plot, and they will emit constantly, continuously over the whole duration of the mission. And we expect tens of thousands of these binaries to be above the LISA noise curve. While the rest of the binaries constituting our Milky Way, that are millions within the LISA band only, will blend together to form this confusion foreground represented here in gray. And finally, you also see some blue stars on this plot, and these are binaries that we have already discovered with the electromagnetic observatories. Here I wanted to list a few reasons why it is important to study these binaries. So the first is that they are guaranteed gravitational wave sources and likely to be the first one that LISA will detect. Secondly, their signals will overlap with all the other LISA sources, so it is important to model them to quantify to what degree they will affect the detectability and the parameter estimation of the other LISA sources. Then, being monochromatic and very loud, they can be used for calibration and verification of the LISA instrument. And finally, because of their unique science that they will provide to us. And just as one example that I will be focusing in this talk is the fact that they will make LISA an all-sky galactic gravitational wave survey with capabilities complementing existing electromagnetic space-based and ground-based observatories. So let me show you briefly what are these binaries composed of. So the absolute majority of those purple points on the LISA plot will be composed of white dwarf stars. And this is simply because of the initial stellar mass function that favors lower mass stars that are white dwarf progenitors compared to high mass neutron star and black hole progenitor stars. And because of the long time scales on which white dwarf stars evolve, so that can take from a few giga-years to the whole age of the galaxy, so 13 or so giga-years. And LISA will see these double white dwarf stars in a detached configuration and in a accreting configuration that is indicated here as IMCVN, that stands for IM Canum Vanaticorum stars. And this is a type of a cataclysmic variable in which both donor and accretor star is a white dwarf. Then again, on the bottom left, you have white dwarf with the helium star companion. And these binaries are very special gravitational wave sources because, technically speaking, helium stars are not composed of degenerate matter like other binaries on this plot, but of the ordinary matter, like our sun. But unlike ordinary stars, these are small enough to fit into compact orbits so that they can emit when in binary, they can emit at the LISA frequencies. And this is because most of the envelope of this star has been stripped during the evolution. So we can think about these binaries in a way as of living gravitational wave sources. Then on the top right, you have the artist impression of the binary pulsar, with which I wanted to represent the class of the double neutron stars. And finally, I also added the binary black holes here. And of course, you should imagine all kind of mixed combination of these binaries, for instance, white dwarf neutron stars, white dwarf black holes, and that, for instance, when accreting, we can observe as low mass and high mass X-ray binaries, and so on. Today I will focus only on this, on the binaries composed of two white dwarfs that I will indicate throughout the slides as DWDs. And I work on these binaries because among the other LISA detectable binaries, we can use them as galactic tracers. And this is because they are numerous and widespread. We can detect them everywhere in the galaxy. For many, we will be able to measure distance directly from gravitational wave signals. And compared to electromagnetic tracers, such as main sequence turn-off stars or giant stars, LISA sample will not be affected by contamination in the sense that any other gravitational wave source that LISA will detect in our galaxy can work exactly in the same way as double white dwarfs. And now to understand how can we use them as galactic tracers, I need to assemble a synthetic population. And for that, I need four ingredients. The first of which is a double white dwarf evolution model, binary evolution model. And in my work, I use models constructed by Sylvia Tonen, based on the binary population synthesis code SIBA. And this model are carefully calibrated against observations in terms of the local number density, so the one observed in the solar neighborhood, and the mass ratio distribution that and the plot you can see on the left. So you have the orbital period, the logarithm of the orbital period on the x-axis and the mass ratio on the y-axis. So our models are in gray, and the black points here are observation available that were available in 2012. And you can see that the two nicely overlap. Next, we need to add to that a recipe for the Milky Way itself. And here the choice comes to the specific feature that you want to study. For instance, you can use smooth analytical functions to represent Milky Way potential and density distributions. You can go for high resolution cosmological, high resolution hydrodynamic simulations. Now, for instance, if we want to look at the details like spiral arms, the bar, or if we want to look at the big picture, we can use cosmological simulations.
Hi, Valeriya. Excuse me, I have a question. You said 2 slides before that we could measure the distance directly from LISA measurements.
Yeah.
But so double white dwarfs are almost monochromatic sources.
Yeah.
So usually you can get the overall amplitude, but which is a combination of chirp mass and distance. But how do you get the distance itself?
Yeah. So being quasi-monochromatic, there will be a part of this sample that will have measurable chirp. And that part is significant enough. I will show the numbers so that we can have a statistically representative sample for all the studies. So it's true for, let's say, it is true for the third of the sample that amounting to tens of thousands. Even a third of it is big enough for the studies.
Okay, thank you very much.
Oh, sorry for not being very clear. Okay, so we have for constructing a synthetic Milky Way, we need the binary population synthesis model or binary evolution model of any kind. The Milky Way, the recipe for the Milky Way itself, then the recipe for the Milky Way star formation. And this is because the star formation affects the distribution of orbital periods of the binaries at the present time. And again, depending on the study, one can one can choose from several options. For instance, analytic or empirical relations, chemospectrophotometric models. One example you see on the left. So this is a summary of one of these models in which you have star formation rate as a function of time for the bulge and the disk. And I use this specific model for almost all of the studies I will show you later. And finally, if you are using cosmological simulations, you have the star formation history there for free in terms of the ages of the stars or star particles. And the very last piece is the actual LISA simulator. As I mentioned before, no gravitational wave signals of these binaries, to a good approximation, can be treated as quasi-monochromatic with the only linear frequency drift. But nevertheless, their identification in the data will be challenging due to the high number of sources expected to be in the LISA band, and to the large number of parameters needed to describe each individual source. So on the right, here you have represented spectral density as a function of frequency. And the gray line there represents one of my mock population. So each vertical line is actually a binary system. And already from there, you can imagine that it is difficult to identify the true number of signals at any given frequency. So several techniques have been developed to address this specific challenge by the LISA data analysis group and separate groups as well. And a few pipelines are available to address this problem. So for example, in this plot, I used an iterative technique that uses a median smoothing of this power spectrum, and then progresses removing binaries with the signal to noise threshold above, with the signal to noise ratio above a pre-established threshold, and repeats this procedure until the whole thing converge. So in color lines here, you see different iterative steps. In each of them, binaries above the threshold have been removed from the sample. Yeah, so this, of course, this method is not fully realistic, as it assumes that we can resolve signals above the threshold. Of course, the reality will be complicated, but this method allows studies like I'm going to show you in the next slides, where I have, several catalogs, each of the catalog consisting of tens of million binaries. So thanks to this kind of simplified techniques, we can work on these catalogs quite fast. Okay, so I listed 4 ingredients for getting, mock LISA population, and now this is the result of these 4 steps. And this specific catalog was constructed by my former master student, Martijn Wilhelm, based on a high-resolution hydrodynamic simulation that has been designed to reproduce the Gaia observations, and specifically the the bar and the spiral arms. So the green points are detected binaries. On the background, you see the artist impression of how our galaxy looks from above. And the red triangle here is LISA itself, of course, not to scale. So already just by looking at this plot, you can understand that LISA will be a powerful tool for mapping our galaxy, and that it will give us a more complete, in terms of surface coverage, survey than optical ones. So here I wanted to show you the comparison with Gaia. And Gaia, even in 2030s, will be the largest optical survey of its kind. Of course, optical surveys affected by different selection effects can see significantly more stars, but their observable volume is limited to our side of the galaxy. While with the gravitational wave, we measure directly the amplitude of the waves that scales as 1/distance, and that allows us to access much larger volume. Plus, we aren't affected by dust, so we can see sources at all galactic latitudes, and we can pierce through the central region that is heavily extincted, so we can see also sources on the other side of the galaxy. And just to give you some numbers, in this specific simulation, we found 25,000 binaries detected above the threshold for the 4-year mission. As I was mentioning before, 30% of this sample, something like 8,000 out of the 26, we found to have a relative error, fractional error on the distance to be less than 30%. And within that part of the sample, the sky position error for LISA was less than a few degrees. And this kind of error bars already allows us to perform galactic studies. So now let me show you what we will learn from the LISA data. So in this first study, I wanted to show you, I've generated mock LISA catalog using smooth analytical functions to distribute binaries, to assign positions to the binaries. And specifically, I used an exponential disk and a spherical bulge. And in these two panels, on the side, I've divided detected binaries in the bulge and in the disk based on their recovered location in the galaxy. So I've binned the detections in spherical shells on the top and in cylinders in the bottom. And so the observed density profile is given by the magenta points with the error bars. Now, by fitting this observed profile with the function that I've originally used to generate this population, and that is here is represented as a dashed black line, I was able to recover back the bulge scale radius to 2%, the disk scale radius to 3%, and in addition, that I'm not showing here, I also was able to recover the disk scale height. And all these three measurements are competitive with currently available ones in the literature. Now, in addition to gravitational wave signals, we've also simulated their electromagnetic signals of these binaries. And we found that a few tens can be identified as eclipsing in wide optical surveys, for instance, like Gaia or LSST. So for these multi-messenger detections using gravitational waves distances in combination with the electromagnetic parallaxes and sky positions, we can narrow down much better the location in the Milky Way. So that information goes on the x-axis from the x-axis side. And then we can use proper motions. So the change in the position on the sky of the binary over time. And we can use that to compute the circular velocity of the binary in the galaxy. And that information goes from the y-axis side. So in this way, we were able to construct this a kind of multi-messenger rotation curve of our galaxy. So the black points are our simulated data, and the lines represent the rotation curve model that I used to generate this mock data. Where colored lines are the contribution from different components of my Milky Way, and the black line is the total rotation curve. So now if we fit simultaneously those density profiles from one slide before and the rotation curve, in addition to the scale parameters, we can also recover the masses of the bulge and of the disk, and those are the posterior distributions that you see on the right. So this study was that I actually conducted with Enrico was a proof of principle showing that by combining very little information from both gravitational wave and electromagnetic observations, and without using additional assumption, we can fully characterize baryonic components of our galactic model. Now, in coming back to the simulation that I showed you before, here we want to reconstruct the shape of the Milky Way bar using laser detections. And we want to do this time by studying Fourier transformation of the density of the green points on this map. So now in this in the center, you see the magnitude on the top and the phase at the bottom panel of the M2 Fourier mode. And I'm plotting specifically this mode because it is the strongest mode when you have a bar-like structure. The other modes are either 0 or lower than this one. And I'm plotting it here as a function of galactocentric distance. So again, our mock gravitational wave observations are in black, and the underlying mass profile that we use to generate the data is in blue. So let's look at the top panel first, and you see that the blue line has two peaks. And our data nicely follow this line up to almost 7 kiloparsec. So let's focus on the first peak, and this one arises from the bar, and the shape of this peak encodes bar structure. For instance, the width of the peak is related to the bar length, and the slope of this peak is related to the bar's axis ratio. And if we now look at the phase, you can see a constant segment in the data in the first 4 kiloparsec or so. And that gives us the measurement of the bar length, physical length, while the value of that, the value of the phase gives us the measurement of the bar's orientation with respect to us. And here in this study, by fitting the data with the model, the Fourier transform of the model this time, we were able to recover bars axis ratio to 10%, bars physical length to 1%, and orientation with respect to us to 1 degree. And again, this would be very competitive measurements compared to optical ones, optical and near infrared actually. So now we are moving beyond the Milky Way, and so in my group we were intrigued by the fact that we can see these double white dwarf binaries everywhere in the Milky Way. So together with the bachelor student, we investigated how far can we actually detect this outside the Milky Way. And in this plot, you see the binary orbital period on the x-axis and the chirp mass on the y-axis. And I will show many of these plots next. And here the merger time is shown in color. So indicatively, purple colors here showing merger times larger than 1 megayear, while orange and yellow is less than 1 megayear. Then white squares represent known LISA binaries, just to show you where are they actually sitting in this parameter space. And when you move from that corner into the top left, you find the so-called supernova type 1a progenitors. So very short period and massive double white dwarfs. While the colored lines here representing the LISA detection threshold at the distance of the Magellanic Clouds. So large Magellanic Cloud, small Magellanic Cloud in yellow and cyan, and Andromeda Galaxy in blue. And these curves delimiting parts of the parameter space above them accessible to LISA. So what we can read from this plot is that LISA can detect binaries with orbital periods shorter than 20 minutes and basically any chirp mass in the Magellanic Clouds, and those with orbital periods less than 5 minutes and chirp masses higher than 0.6 in the Andromeda Galaxy. So now you may wonder whether such binaries exist in those galaxies and why we don't see them in the Milky Way. So why we don't have any white squares in that part of the parameter space. Sorry, did somebody have a question? Because I heard some noise. Okay, if no, then I will continue by replying on why we don't see these binaries in the Milky Way. Does it change? Okay. So in a paper led by Alberto Rebassa Mansergras and Silvia Tonen, we looked at the simulated light curves, spectra, and gravitational wave signals of these double white dwarf binaries, and we compared these detection techniques. So let's start from the light curves. So massive short period double white dwarfs are hard to detect as eclipsing because they are faint and because their eclipse is very short due to the compact size of the white dwarf stars. Now, for instance, we saw that they are orbiting in more or less tens of minutes, and their eclipse lasts of minute or so. So it's very hard to get an observation point during the eclipse. During the eclipse. Now, if we go to the spectroscopy, here you see on the slide the H alpha line in a white dwarf, in a double white dwarf spectra, And specifically the top left panel on this slide is showing you the ideal case. And you can notice that it has kind of a double line, and that is the signature that this is a binary. And then you can see all the other panels basically showing you how that line would be observed by different instruments. And just by comparing, you can see that it kind of washes out. So it's actually almost in all the cases. So it's a challenging technique to use for discovering these binaries. And finally, we looked at the detectability and the chirp mass measurement in particular, because we want to say that these binaries are massive with LISA. So here again, I'm showing you orbital period versus chirp mass. And the points are my mock binaries. And the color now is showing the fractional error on the chirp mass. And for your convenience, I'm as a dashed lines here, I'm showing you the relative errors, specifically the blue one of 33%, and the pink one of 1%, and then 0.1%. And here the black numbers are showing, are telling you how many points are in each of these quadrants that these lines form. Oops. And well, you can see that those numbers are quite large, especially when we compare it with zero confident detections today. So, and this made us conclude that LISA may be actually the ideal instrument for hunting the double white dwarf, double degenerate type 1a progenitors in our galaxy, but also in the other galaxies. So how many of these do we expect beyond the Milky Way? And as a simple test, together with Orlin, we looked at the Andromeda galaxy. So because Andromeda is a kind of twin sister of the Milky Way, we would roughly double Milky Way mass. We generated a synthetic population that resembles that of our galaxy, but with twice the mass. And we place it at the distance of the Andromeda. So, and here I'm showing you the result. Again, orbital period versus chirp mass, but now the color showing you the signal to noise ratio. So here I left the merger time as the dotted black lines, and the golden line showing you the LISA detection threshold at that distance. So if you count the points, you will find that for the 4-year-long LISA simulation, we have a dozen of detections. And for the 10-year-long LISA simulation, we have something like a few tens of detected binaries. And we also found that this, the binaries in the Andromeda, so the specific parameter space, has a high degree of completeness, meaning that LISA will detect almost all binaries that are actually there. So now moving into the specific Milky Way satellites, again with another master student, Michael Kane, we constructed a detailed model of the Large Magellanic Cloud. So we started with the observed plane projected star formation history of the LMC. So here you see the image, and each of the pixels in this image has its own reconstructed star formation history. And as it's plane projected, we wanted to give it a third dimension. So we combine this actual optical observations with the numerical simulation that you can see in the middle. And on the right, you see the result. So mock binaries detectable by LISA. And here you have something like 300, 400 binaries. And each binary has an ellipse, and that ellipse is as an error on the sky position. So you can see that the majority of those ellipses are very small. So LISA will actually spatially resolve the Magellanic Cloud in gravitational waves. And it means that we'll have a lot of opportunities now for LISA studies for this galaxy. But what about other satellites? And now I'm looking only at the hypothetical satellite for which I vary the total stellar mass on the x-axis and the distance from us on the y-axis. And the color here telling you the number of detected binaries in this parameter space. And again, for your convenience, just roughly, I'm showing you with this dashed line where the one detection contour lies. So from this plot, what we've learned is that we can detect, well, LISA can potentially detect satellites with stellar mass of higher than 10 to the 6 if they are located within a couple of 100 kiloparsecs from us. So as an example, we have their Magellanic Clouds, Sagittarius galaxy represented with stars. And I will show you in the next slide that LISA detections can inform us about the global properties of the satellites. But what this plot also tells you is that we can potentially discover new satellites. For example, if our satellite galaxy is hiding behind the disk or the bulge of the Milky Way, and therefore is inaccessible with the electromagnetic observatories. So in this companion paper led by Eleanor Rober, we studied the sensitivity of LISA to a fiducial source with the set chirp mass, frequency, and inclination. And we placed this source in all the known satellite galaxies. So in the sky map, you see the density of the foreground, so Milky Way sources in orange, and the stars and points are the satellites. The stars are those in which we were able to recover our fiducial source, and the points are in which the source was not detected. And the shades of blue are showing you the sky uncertainty that we measure. Finally, just to combine the two studies that I showed you in these two slides, we circled the satellites in which we expect more sources than the galactic foreground, and that we potentially that we can recover with the detailed Bayesian data analysis. So again, we have Magellanic Clouds, Sagittarius, Kuiper Galaxy, and perhaps even Fornax Galaxy. So how much time do I have at this point?
I would say you have 5 minutes left. And then if you want, maybe you can cut a couple of minutes from the question section. I don't know how long it will take for the next slides for you.
I think that this is one last result on the galaxy, and then it depends how many questions do you have. I have a bonus point, but yeah, I think that I can do it within 5 minutes.
Okay, great.
Okay, so then the final measurement that I prepared for you today is the mass of the satellites based on the LISA detections. And we can study this by now reverse engineering the modeling procedure that I used in all the previous slides. So for example, we can start from the number of detections and the distance measured by Lisa. And we can use our models that I've constructed in the previous slides that predict the number of detections per solar mass, in which I vary the age of the galaxy, distance, and star formation. And based on the input number of detected sources, I can reconstruct in a Bayesian way how much mass was needed to get to that number. So, for instance, in this last panel, I'm showing you how accurate our results can be. So if the true star formation of the satellite is known, for instance, from electromagnetic observations, and that is the case of the orange curve, we can recover the mass of the satellite within the factor of 2. While if the star formation history is unknown, we can use several of those, and we can marginalize over them, and that's shown by the dashed gray line. And in this case, the mass can be constrained to within an order of magnitude. And actually, even if no detections were found in the LISA data, we can still place an upper limit on the satellite's mass using this same method. So importantly, LISA will provide an independent measurement with an uncertainty that must be accounted jointly with electromagnetic observations for the satellite's masses. So I guess this is the main take-home message that I want you to take home, and specifically that the LISA is an all-sky will be an all-sky galactic survey that will deliver, a number of guaranteed results. And as a bonus, I wanted to show you that we can also use this double white dwarfs binaries to trace other astrophysical population, such as circumbinary exoplanets. So here you see the artist impression of such a system, in which we have a central double white dwarf and exoplanet orbiting around it. So at present, we actually don't know of existence of these systems, but we know that, and we observe that exoplanets orbit white dwarfs and they orbit binary systems. So we expect that it will be possible also for double white dwarfs. And we can look for them in the LISA data through the frequency modulation that they introduce into the double white dwarf signal. And that works in the same way as FM broadcasting. So in this case, double white dwarf signal would be as a carrier, and the circumbinary exoplanet would add a larger modulation on top of that signal, so that we can create a different pattern here. And by looking at this kind of patterns in the data, we can understand whether there is a third body orbiting our monochromatic binaries. And specifically, Nicola Tamanini and Camilla Danielski calculated what parameters of this tertiary object LISA can access through this technique. So on the x-axis, you see the distance of exoplanet from the center of the mass of the binary, measured in astronomical units. And on the y-axis, you have the planetary mass and Jupiter masses. So all the gray markers are known exoplanets, and all the colored lines are the sensitivity curves of different observatories and techniques. And we are looking at the red ones that are that are showing the parameter space accessible for LISA. And the difference between the curves consists in the signal to noise of the inner double white dwarf binary and its frequency. But roughly you can see that in this way we can detect tertiary objects that are more or less at 1 AU from the central binary, and that are more massive than Jupiter. And to estimate the detection rate of these systems, we injected exoplanets into the one of the mock catalogs that I showed you before. And for that, we used several observationally motivated scenarios. So here I'm showing you only the most optimistic and the most pessimistic one. So on these plots, we have in green, we have double white dwarfs with the brown dwarfs as the tertiary companions. And in red, we have double white dwarfs with exoplanets. And in this study, we use as a parameter that distinguishes between white dwarfs and exoplanets is the mass of 14 Jupiter masses. And just for comparison, you also have the other colors are showing you different detection techniques available nowadays. So again, you see that we expect from a few to many to several tens of detections, depending on what is actually what is the recipe, what the recipe was used. And as a big advantage compared to the other detection methods of these tertiary companions is that you can see them, you can detect them as far as LISA can detect double white dwarfs, so everywhere in the galaxy. And that would be possible also in the satellites, but only for the most massive ones. And these are my conclusion points. So I showed you that LISA will be an all-sky survey, and that it doesn't suffer from contamination, dust extinction, and therefore can be used to map the entire Milky Way and its neighborhood. I showed you that we can use density distributions of LISA binaries, LISA detected binaries, to constrain scale parameters of the Milky Way components. I also showed you that we can detect with gravitational waves Milky Way satellites and potentially discover new ones that are invisible to electromagnetic observatories. And we can weigh those satellites by LISA detections. I also showed you that LISA may be our best tool for testing the double degenerate formation channel for type 1a explosions, and that will be possible in the Milky Way and in the local group. And finally, that we can use LISA, monochromatic LISA signals to trace other astrophysical populations, such as circumbinary exoplanets and brown dwarfs. And with that, I will be happy to take your questions.
Okay, thank you very much, Valeriya, for the very nice talk. So we have, I think, time for a couple of questions.
Can I ask a question, Nicola?
Yeah. Go on.
Yeah. So pertains to the last slide you showed about the exoplanets. So there, I think you see the effect, I imagine, of the acceleration of due to the three-body system. So the effect of the acceleration is there also in principle for double white dwarf systems in the galaxy, because the system moves around the center of the galaxy. Is that a tiny effect? I mean, there's that, and also in principle the Doppler shift due to the peculiar motion of the binary. Are those unobservable effects? And if so, do they bias your results? Or do you ever consider those, or do you just consider plain vanilla waveforms where those effects aren't?
Yeah, in this, so this is a big project that we set up, and this first study was actually the vanilla waveforms for now, but we are developing, this study will be more and more robust with the Bayesian detection and parameter recovery of the acceleration and so on. So we are working on making it as detailed as we can, given our available tools.
Yeah, I think shouldn't the tools be the same as for the exoplanets in principle? I guess, I mean, I don't know how you compute the waveforms, but I imagine the main effect there is the acceleration, so low order.
Yes, and here we didn't split the acceleration in any possible other, due to any other possible contributions. But of course, it's a very fair point. We have to test, how this can be affected by other effects. And in particular, you mentioned the acceleration due to the motion in the galaxy, right? And that should not affect binaries. That should not affect binaries with that should affect binaries only with the high chirp mass, where we actually so precise that where we can be so precise that that the effect starts to be measurable. Yeah, so that is one certain point that I can add to this, and I agree that we should add. We should.
Yeah, you have to start from somewhere. I mean, this is okay as a first step. I wanted to ask one or maybe two other questions, but I don't want to ask all the questions if there's anybody else.
There is Sebastian who raised his hand.
Yeah, so let's go with Sebastian first.
Yeah.
Okay, hi, can you hear me?
Mm-hmm.
Okay, well, first, thanks a lot for this very nice talk. My question is, in the beginning, you said there are some assumptions on how well you can extract the signals. And I know that, as I said, it's a big problem. So how much of the things of the physics that you show do you think can be done in principle with the tools available at the moment to analyze the data? And how much more is needed to reach the state that you presented here?
Okay, that's a good question. In a way that okay, so for galactic binaries, we are very, like, even with the primitive estimates, given that we are exactly in the best position in the LISA bucket, we are exactly in the millihertz, and even in the worst case that can happen, maybe we don't resolve all the binaries, or there is more foreground that we expect. These large numbers of detections that comes basically just from how massive the Milky Way is, so they cannot be totally different. So the order of the magnitude comes from the mass of the Milky Way. I would still expect, even if our data analysis tools perform much worse than I showed, I would still expect thousands of binaries with with good enough measurements. So I think that on this side, for galactic binaries, I feel safe. And indeed, like in the LISA studies for the figure of merits that show you like how much instrument modification you can allow to make science possible or not. And yeah, galactic binaries are very safe. So
okay,
yeah,
thanks.
I guess we just need to improve on the tools, because mainly because we don't want these binaries affecting other sources that are more complex.
Okay, thanks.
Okay, then Enrico, if you have
very briefly. Yes, I have two more questions. One, which I believe I asked you in the past, but I'm not sure about the answer, and maybe things change with the latest models that you have. You focus on double white dwarfs. But in principle, your model is a population synthesis model, so you have all sort of binaries. How many do you predict that LISA will be able to see any double pulsars in the galaxy? Because that, of course, if we could observe a source in LISA and with radio telescopes, that would lead to a much more precise data analysis. And this is the first question. The second is, it's again in the way of possible systematics do you expect that any of these systems, for instance, the progenitors of type 1a supernova, will have mass transfer, and would that affect the frequency evolution?
Okay. Okay. So regarding the double pulsars, for instance, so in my models, I go as far in the IMF so that I have only white dwarf stars, but from the literature, roughly the numbers scale as like for the double white dwarfs, you have tens of thousands. Then if you want those double white dwarfs to be close enough so they accrete, you go down in the order of magnitude, so you have thousands. And if you want double neutron stars, you go again one order magnitude low. And then, of course, then the exact numbers will change with the models. But I would, for the double neutron stars, the highest estimate that I have seen in the literature was like a couple of hundreds. But now with the LIGO that providing, that the error measurements on the binary neutron star merger rate is shrinking, we will be able to narrow that down better. But unfortunately, like it seems like it will go
even lower.
Yeah, it seems like it will go below the hundreds. Yeah, so this is roughly how it goes with the different populations.
I see. Okay, and so you expect only a few hundred to 1,000 will have mass transfer.
Yeah.
Okay.
Yeah. So again,
yeah,
not significant percent, but significant enough that you can do some population studies.
Yeah,
and
you should be aware in case you want to test GR, for instance.
Yes. And I don't have on the top of my mind the author, but there is a recent study looking at the binary neutron stars and the electromagnetic, I think the SKA or something like bigger radio observatories. So I can point that to you.
Yeah, that'd be great. Thanks so much.
Yeah.
Okay, thank you again, Valeriya.